Okay, Bob, describe your area of expertise in geology.
As a geologist, I have worked for the survey most of my professional life, really all of it since grad school. And my work has always involved volcanoes in one way or another, sometimes explicitly working directly on volcanoes, volcanology, or the geology of volcanoes. Sometimes working on tectonic problems that involve volcanic rocks, too. So I've been very interested in how volcanoes and magmatism are related to tectonics. So these are the two areas that I've spent most of my career working on.
Okay, and so where were you educated and what was your degree? And
I graduated both as an undergraduate, my bachelor's degree and my PhD were both from Stanford. I graduated in 1956, got my PhD in 1961 in geology, not in volcano studies, however. I was working in metamorphic petrology and structural geology at that time.
And how was it that you began working in Yellowstone?
I was one of a group of people who started working in Yellowstone in 1965. And the impetus for this was that Yellowstone had really not had a comprehensive geologic study since the late 19th century. Surprisingly enough, there had been individual specific topical studies, but there hadn't really been an overall comprehensive study of Yellowstone's geology in the modern era. So a group of us were tapped to undertake a new geologic map of Yellowstone. We were divided into 5 teams, and rather than just each one mapping his own area, which is often the way this sort of thing might have been done in a joint project like that, each person with a separate quadrangle, we actually worked in topical areas within the overall framework of Yellowstone geology. And so I was asked to organize a study of the young volcanic geology of Yellowstone. So there was a group of people doing the early geology, the pre-tertiary geology in the northern part of the park, a different group of people working in the southern part of the park on the same kind of thing, another group working on the early tertiary volcanic rocks, which is a completely different problem. Then I and some colleagues worked on the quaternary volcanics, the young volcanics. And then there was yet another group of people studying the glaciation and related superficial geology. In addition to that, there were some other topical studies that went on simultaneously, including the geothermal studies that included drilling, isotopic studies, isotopic geochemistry, which was usually coordinated with the geologic studies that we were undertaking at that time. It came about because their funding became available to do this through a cooperative program involving the USGS, NASA, and the Park Service. Most of the money actually came from NASA. And their interest in it was they were at that time just developing a lot of the remote sensing instruments, which ultimately went into satellites and also into interplanetary probes. But they needed test areas where the geology was well known, where they could calibrate this instrumentation. So most of this was done with some of these instruments flying in aircraft. And then Yellowstone was one of several of these so-called ground truth areas, and that was the reason we got started on it at the time we did.
Describe how you felt the first time you saw LiDAR of Yellowstone.
Well, I mean, LiDAR is such a marvelous new technology. When you see the imagery, it's just different from any other kind of imagery we have. We had radar imagery and of course lots of different forms of aerial photography. But this LiDAR imagery shows details of the ground surface that you simply can't see. Sometimes you can't even see in the field because the features themselves are bigger than what you're actually seeing right in front of you, and other things like trees are in the way. So when you actually see it that way, it's really quite a, particularly when you are first seeing it, as you suggest, it's quite a spectacular thing.
How many years did you work in Yellowstone?
working there?
Well, I worked in Yellowstone intensively for a short time in the fall of 1965, but then every summer for about 3 months during the summer months from 1966 through 1971. So that was really when the bulk of the geologic mapping was done. And it was in Yellowstone and in some of the adjacent areas outside the park, because the geology didn't magically stop at the straight line park boundaries. So it included work down to Jackson Hole and over into the eastern part of the Snake River Plain as well. Then after that, after doing other things and then interspersed with other USGS assignments of one sort and another, I continued to work in Yellowstone for the next 25 years. But usually then it was in shorter increments in the field, a lot more involved in looking at the chemistry of the rocks and thin sections and looking at, again, at specific topical things, more collaboration with other geologists on the geochemistry and so forth.
What role did collaboration play in your work?
It was very essential. The interaction among the people working both in the field and then with our other colleagues who were doing lab type studies. The whole project really came to fruition because of this very intensive collaboration and the focus of a number of groups at the same time working on the same overall problem of Yellowstone's geology.
Were there epiphanies as the geologic story of Yellowstone began to unfold?
There were some epiphanies, so to speak, in terms of what we learned as we were going through this, particularly during this initial period, this 6 years of intensive field studies. I was very fortunate in that my particular area of study, the young volcanic rocks, there had been a fairly recent study, a PhD study by Joe Boyd, who became a geophysicist at the Carnegie Institution Geophysical Laboratory. But his PhD thesis had been to study some of these same rocks that I ended up studying with some of my colleagues. And he had done a wonderful job. I mean, considering that this was a thesis project and starting from scratch in an area that had really not been looked at all, he studied some of these young volcanic rocks and he really came to some of the big conclusions. That is to say, he recognized that the predominant rhyolitic rocks particularly around the margins of the park and the outer parts of the park, were pyroclastic rocks instead of lava flows. And this was a very important thing, and he was the first person who really recognized that in a big way. In addition, he recognized that there must be some kind of, he called it a volcanotectonic depression, that is to say a structural depression in the central part of the park somehow related to the eruption of these pyroclastics. He didn't have the full picture, what we now recognize as the Yellowstone caldera. But there were still many things that he was not able to recognize in that study. And one of our first big, in fact really something we found in the first day we were in the field, my colleague Dick Blank and I went out to look at a particular locality that Boyd had described quite carefully, and he had interpreted as a vent for some of these pyroclastic rocks, these welded tuffs. It didn't sound right to us from his description, but it sounded like an important locality. So we went there, and on the very first day we recognized that rather than being a vent for the Yellowstone tuff, as he called it, it was two different ash flow tuff units, different in age, and one had been eroded and the other one had filled in some paleotopography that had been formed in that older unit. So from the very first day we got there, we realized we were dealing with more than one major pyroclastic eruption. It turns out that there were 3 of these major pyroclastic eruptions, separated in time by 700 to 800,000 years or so.
Okay, Bob, so tell me, what tools did you use in the field?
Describe
Well, yes, the tools I used in the work I was doing really was basic geologic mapping. The focus of the study was the volcanic geology, but the tool was really geologic mapping. So we used topographic maps, aerial photographs, Brunton compasses to measure various structural elements, rock hammers to collect samples, which of course were very important to us, which would later be either age determinations would be done on them or chemical analyses done on them, thin sections cut. And so collecting samples, putting lines on the maps, working primarily from air photographs originally, and then of course during the non-field times, a lot of it involved the use of various ways of getting the information from the aerial photographs accurately onto topographic maps to actually create the geologic maps as such.
Following the field work, tell me how the data was worked up and published.
The idea was, of course, each of these 5 sort of field-oriented topical studies that were part of the comprehensive geologic framework of Yellowstone. Each of these would be published separately, but brought together in a series of U.S. Geological Survey publications, professional papers. And so they got published at different times over a long interval of time. And mine was actually the last of these to be published because a great deal of further work after that initial intensive period of field study went into that professional paper. So although the field work was done, the bulk of it, probably 85 or 90% of the work was done from 1966 to 1971, the publication didn't come out until 2001. So there was really a period of 30 years of additional field work and additional studies and interruptions in the work with other things taking place, and all the while working on this professional paper. It got to be something of an albatross after a while, but that's the way these things often turn out.
Was there any pressure to publish your work?
I had a great deal of interest in the publication, and I distributed preliminary working copies of it over a period of years as the revisions of the manuscript took place to many colleagues, including not just USGS colleagues, but particularly our colleague Bob Smith at the University of Utah, who's a geophysicist. He and his students were doing a lot of work during this time of this later phase of my work, but they were very interested in having the publication from the overall study of the volcanic geology, and so they were among the people I shared early versions of it with, and ultimately have been able to give the final publications to.
How was it revealed that there were 3 calderas?
We weren't able to fully delineate the caldera structures until the mapping was really pretty well complete. As the work evolved, we got parts of the picture. I would say within the first 2 summers, we had a pretty good idea of the Yellowstone caldera, which is the youngest of the 3. And we realized that it had 2 resurgent domes. It's one of a class of calderas called resurgent calderas, which means that magma coming back into the near surface after the initial partial emptying of the magma chamber and collapse of the surface to form the caldera, came back into it and domed up what had been the caldera floor into a structural dome. And this class of calderas had been identified by another Bob Smith who worked for the USGS and his colleague Roy Bailey, and had been recognized in many places around the world in these large calderas. But this is the first time, I think, that we recognized one that actually had these 2 separate structural domes as part of a single caldera. So it was simply so large that the magma had generated what amounts to 2 ring fracture zones that partially coalesced. We recognized that probably in broad outline after about the second field summer, but we really didn't have the full picture of all the calderas until the geologic mapping was completed. And that's an important thing to realize, is that it's the real structure, the understanding these calderas, where they were, and in fact that there were these several calderas, was learned on the basis of in-the-field mapping, geologic mapping. There's sort of an apocryphal story that has gone around in many different forms that somehow NASA discovered these from space. And I think that stems from this idea that NASA was partially sponsoring this work and funding part of it, a major part of it, as part of their ground truthing of remote sensing instruments. But they did not discover the calderas. The calderas were discovered on the ground by traditional field geologic mapping.
Just to be clear, what was the USGS role in this science?
The USGS role in all of this was really central. I mean, we were the people doing the field work. We collaborated very closely with both the Park Service and NASA. NASA basically provided funding and did some of the remote sensing instrumentation, which we then, our observation, which we then utilized in some of our work. We looked at infrared images, radar images, some of the aerial photography they took. We worked on analyzing some of that data for NASA so that they could utilize, again, use the sort of ground truth concept in understanding the nature of the data they were getting in these instruments. So the USGS was really doing the hands-on work of what was in the field and relating the field work to the imagery. The Park Service's role was primarily in wanting a comprehensive study done for their own interpretive program so that they would have better, newer information that they could pass on to the public. And so they were very interested in getting this information, and they were very active in having us work with their staff, for example, in giving them background talks and sort of thing, and actually working with some of the naturalists in promoting how to present some of it. But really, I would say that it's the USGS that was the active partner in actually doing most of the work on site.
So were there seminal publications of USGS geologic findings for Yellowstone?
Okay, one of the first publications that I think caught some general attention was one that was published in 1975 in the journal Science. And it was an attempt to bring together what we had learned now on the basis of our initial period of fieldwork and understanding the general picture of the volcanic evolution of Yellowstone in the latest Cenozoic time, say in the last 2 million years roughly, and bringing that together with the geophysical data, which had also been acquired during the same period of time using some of the same sources of funding. So we had a new geologic map, we had a new gravity map, we had a new aeromagnetic map, a certain number of seismic studies had been done, that is passive studies, studying earthquake distribution, seismicity in the park. And so bringing this information together and interpreting it enabled us to interpret not only the surface geology, but how it was related to what we felt was the subsurface magmatic system. And so this was brought together, I think for the first time, in a paper published in 1975, in which we felt that we had, in a number of ways, at least partially imaged the magma chamber that underlies Yellowstone and is both the source of the major volcanic eruptions that have occurred there over this 2 million year period, and the major source of the geothermal heat, which of course is what Yellowstone is best known for, is its hydrothermal systems.
How was Gordy Eaton involved in this journal Science publication?
The person who actually brought this paper together, that is, gathered the various elements of the data, particularly the geophysical data, and worked with me then on the geologic interpretation of it, was Gordon Eaton. And at that time, Gordy was working in Reston for the USGS headquarters, and was, I think, a little frustrated by the fact that he wasn't able to do much field work. But when he started to see some of this geophysical data, particularly the gravity map that had just been compiled, he became really excited about it and recognized that the gravity map itself was showing a big subsurface system related to the Yellowstone caldera. And so he was the one who sort of then gathered together the other geophysical information and worked with me on the geologic interpretation. So Gordon Eaton was the primary author of that multi-author paper. All USGS people, however, who were contributing to it.
When did it become apparent that the caldera was inflating?
Yeah, probably one of the most interesting additional pieces of data that came along after this period of time we've been describing with the early field work, more or less the completion of the initial geologic studies and doing the geophysical interpretations that helped understand the subsurface part of it. Bob Smith at the University of Utah was interested in seeing if we could look for signs of contemporary deformation in the Yellowstone caldera. He had recognized some of these indications, particularly in changes in lake levels in different parts of Yellowstone Lake, which is a very large lake. And because it's so large, and of course water tending to always seek a level, he felt that there was indications that the lake basin itself was being tilted. And because of this, the lake level was rising at one end of the lake and falling at the other end of the lake. And he was interested in seeing whether we could actually measure this by some direct means. So one of the things I did, at that time I was in an administrative position in the survey. I was the coordinator of the USGS geothermal program. I managed to get funding together to get the USGS topographic division involved in a re-leveling. They had leveled the road network in the park. That is, surveyed it using level instruments which gave a series of elevations on all the roads in the park back in the 1920s, I think 24 and 25 if I remember correctly. And there had not been a re-leveling since that time. We felt that with as much deformation as there appeared to be based on these lake level changes, that there should be measurable changes in elevations in the park. So we finally got the funding together and got that survey done, and the data was provided to Bob Smith and his group at the University of Utah, and they in turn integrated all this material into a series of elevation changes, the map of elevation changes throughout the caldera, and demonstrated that in fact the caldera in the roughly 50-year period of time between these two surveys had come up about 2/3 of a meter, a couple of feet, and correspondingly less elsewhere, so that it was a dome-shaped uplift that had taken place during this 50 years. A rather spectacular amount of uplift, indicating that the magmatic system in some form was active. Either the magma was actually intruding the crust, or it was heating the hydrothermal system and causing it to expand and elevate the crust. Something was going on. Subsequent to that, there have been additional surveys which showed that in fact then after a period of continued uplift over the next decade or so, there then was a period of stability for about a year, and then there was subsidence. So we now know that the Yellowstone caldera is not simply going up, but it goes up and down in a sort of breathing motion apparently at times. Its overall deformation does seem to be an inflationary one, but it's not a steady sort of thing, and there are in fact periods of deflation.
How does the Yellowstone story fit in with things like the Columbia River flood basalts to the west?
Yellowstone, we now understand, is the contemporary expression of a system that has been active in the Earth's uppermost layers, in the upper mantle and lower crust, that has been active, magmatically active, over a period of at least about 17 million years. The earliest expression of this appears to have been related to the vast outpouring of basaltic magmas in the form of big basalt lava flows that covered the Columbia River Plateau. Most of them erupted from the eastern part of the plateau in the northern Rocky Mountains of eastern Idaho and western Idaho and eastern Washington, but flowed across the Snake River, the Columbia River Plateau, essentially filled the plateau and spilled through the Columbia Gorge out to the coastal region along into the sea. So this vast outpouring of basalts over a very short period of time. Really, the biggest bulk of those came out during less than 1 million years, around 17 million years ago, roughly. That was the first expression of this, but then the later expressions have been more or less along a linear trend, which is now represented by the eastern Snake River Plain. Beginning in southwestern Idaho, about 14 or 15 million years ago, and continuing through southeastern Idaho, right up to the Idaho border and then into Wyoming. And as I say, the current expression of this so-called hot spot is the Yellowstone Plateau magmatic system. But we can find evidence that similar systems of mainly rhyolitic magmas but associated basalts of earlier ages form a chain of calderas now buried by younger basaltic lavas along the eastern Snake River Plain. So the origin of this so-called hot spot is a subject of great contemporary interest and some dispute in the geologic literature.
What is the connection between the Grand Tetons and Yellowstone?
Yellowstone, although it's actually in the Rocky Mountains, is really much more related to the Basin and Range Province than it is to what we typically think of as Rocky Mountain geology. Rocky Mountain geology, for the most part, goes back to what we call a Laramide and earlier, which is the latest Mesozoic, let's say roughly 65 million years ago to something back even 70 million years and earlier. So that geology is sort of a framework, but the basin and range geology, which mostly is expressed in Nevada and western Utah and surrounding parts of Oregon and Idaho, actually encroaches into the Central and Northern Rocky Mountains. And Yellowstone is right where that impingement of the basin range tectonics, ongoing active tectonics, extensional faulting and spreading of the Earth's crust, intersects with some of these pre-existing structures. And so the Tetons are an expression, the Tetons as we see them now are an expression of this basin and range topography, which in turn is an expression of basin and range faulting, with the Jackson Hole being the downdropped block and the Tetons themselves being the uplifted block. If this were in the middle of Nevada, you would think of it as nothing different than the Toyabe Range or some other range and valley system in the Central Great Basin.
How has evolving technology affected your work?
My own work has been primarily on the geology, both the field geology and then looking at some of the analytical work we do on samples collected in the field, both chemical and age determination, working with colleagues on those things. But most of the technological changes in what we've been able to do and been able to learn about the Yellowstone magmatic system have been more in the geophysics. So we now have much better seismology, for example. We have digital broadband seismic instrumentation, whereas we used to simply have analog, sometimes just one component, sometimes three component seismometers. Particularly the deformation studies, which we used to do primarily by leveling, are now done by GPS measurements in the field. And a number of other additional developments, including things like using satellite photography, comparing different satellite images and getting interferograms, as they're called, which show the difference, changes in surface features, which again reflect some of this uplift and subsidence that we talked about in the Yellowstone caldera.
How did you collaborate with your USGS colleagues during field work?
Well, certainly one of the joys of that period of time, particularly in the mid to late 1960s, when we were working as a group of teams, really, in the field, we frequently got together. And even though we were working on different topical elements, there obviously are very strong interrelationships among them. And so we were working with the people and getting together, both in a kind of in-the-field socialization kind of thing, as well as scientifically interacting with these other teams. In particular, with the group of people studying the geothermal systems, the hydrothermal activity. Don White, Bob Fournier, Patrick Muffler, and Al Truesdell were the four people doing physical and geochemical studies of the hydrothermal systems during this period of time. And because that's so intimately related to the young volcanism that was my primary field of study, we spent a lot of time together and looking at each other's work and seeing how what each of us was learning separately helped the others to understand the framework of their own work. So it was a particularly good time, both scientifically and just in terms of good comradeship.
Did you learn things from the drilling that clarified the caldera story?
One example of the kind of thing that we learned from the drilling studies, which of course were done to study the hydrothermal system, but they made continuous core drillings of the entire holes that they went into, which were sometimes just 100 feet or a few tens of feet, and sometimes many hundreds of feet. The deepest one I think was 1,300 feet. So these were a great opportunity for us to see some of the subsurface geology that was otherwise inaccessible to us. So not just the geophysical studies that were done too, but some of the shallow subsurface we were able to observe directly. The most interesting aspect of this was a particular drill hole in the lower geyser basin, or the Midway geyser basin as it's called, in the western part of Yellowstone, where we had interpreted that there was a resurgent dome in the western part of the caldera, but could only see the young rocks that had covered the original caldera floor being uplifted. We were able to interpret the fact that there were actually two episodes of uplift, one very close to the time of subsidence. Caldera subsidence occurred, and very shortly afterwards there was inflation to form the resurgent dome. on the basis of a drill cord that was put down there which showed that there was in fact Lava Creek tuff, the 600,000-year-old tuff, present within 10 meters of the surface, within about 30 feet or so of the surface, which was not to be seen at the surface anywhere. We had expected it would be there, but to actually have it and to get samples of it and be able to know which unit it was and so forth was a particularly useful thing to us in interpreting the structure of the caldera.
Did you encounter any wild animals during field work?
We, meaning Dick Blank and I, who did most of the mapping of the young volcanics, were very lucky in not having any serious encounters with wild animals. We did encounter them and were able to maneuver in such ways that they were never a direct threat to us. But there were a few times when it became a little scarier than you would really like. One episode I remember in particular with a field assistant being out in a backcountry area and coming up a trail on our way home after spending a long day in the field and being very tired, and on our way down the trail on our way home. And here was a grizzly bear. We came around a corner and there was a grizzly bear sitting right on the trail as we were headed there. And as we came around the corner, this grizzly bear stood up and looked at us, and that was not a particularly comforting sight. Fortunately, the bear decided that we either weren't interesting or he didn't want to mess with us, or we certainly didn't want to mess with him. So the bear turned around and went away, and after some misgivings, we finally did decide to walk on down that trail. So those near encounters are entertaining, if you will, in retrospect, but we never felt we were in direct danger.
Oh, you're lucky.
Yeah, right. There were others. There were other people who did have encounters, and one of the things that, because of what we were doing, Dick Blank and I did not use helicopters. We did everything we did on foot. However, some of the other people working in the park did use helicopters, and there was one instance where the glacial geology crew actually were working with a helicopter. The pilot decided to have his lunch in the helicopter one day, and so then when everybody was off in the field, a bear got into the helicopter and totally tore it up from the inside, and in fact destroyed the helicopter basically, so it had to be flown out with assistance later.
Did your family spend summers in Yellowstone as well?
During that first 5 or 6 summers of intensive field work, my family came out with me in the field every summer. So we would usually drive from Denver, where I was living at that time, up to Yellowstone, which was for us typically a day and a half's drive. You could do it in a day, but we usually chose to extend it a little bit. So in a day and a half, we would get up there. The interesting part of this was we had 2 little boys. We had twin boys who the first summer we went up there in June were about 9 months old. So they were still crawling. We were to have a brand new government trailer as our permanent quarters, but it had not yet arrived. So we were more or less stuck in what they called camper cabins in the Old Faithful area. These were really kind of dingy, old, concrete floored log cabins with heated only by a wood stove. And the floors were so dirty, my wife wouldn't let the boys crawl around on it. So what she did was build a little playpen with suitcases around the double bed. And the boys spent about the first week playing on this double bed. And my wife and it turned out it rained a lot during that particular week too. So indoors was pretty much the order of the day every day for several days in a row. By the end of that week, my wife was somewhat near wit's end when our brand new house trailer finally arrived. So we all of a sudden moved into this trailer, which probably if we had started directly in that trailer would have seemed very cramped and small. But at that point, it was clean and new and big, and it just looked wonderful to her. So that was actually almost a slight benefit of having had to spend that rather miserable first week in the camper cabin.
How old were your boys?
The boys were 9 months old when we first went to Yellowstone. They had their first birthday in the park before we came home in September of that year.
What were your favorite sort of locations?
Well, I think a couple of my favorite locations in terms of the geology. The park as a whole is such a wonderful place that I don't have any particular favorites just in terms of what areas I like. But in terms of geology, there's one particular place that really stands out, is Mount Everett, which is an area just east of Mammoth Hot Springs. And this is the locality I referred to earlier where Joe Boyd had thought there was a vent for one of the welded tuffs, but where Dick Blank and I actually went on our first day there and found that in fact what it is a place where the base of the Huckleberry Ridge tuff, the 2-million-year-old tuff, is well exposed, sitting on gravels in a paleo valley. But then this whole thing had been cut through by a younger canyon, a canyon of Lava Creek, and the younger Lava Creek tuff, the 600,000-year tuff, had then come into the eroded surface of the Huckleberry Ridge. So what you can see there is the gravel at the base of the Huckleberry Ridge on erosional surface, the Huckleberry Ridge itself, well exposed with its vitrific base, its glassy base, and then the erosion that cut into it, and the Paleo Valley, with a soil developed on it, and this younger ash flow tuff that comes into it, actually incorporating talus off of the older flow, and having come in and chilled against it, so you again get a glassy margin to the younger flow where it contacted the older pre-existing ground surface. It's just a great place to see these kinds of relationships, and I've taken many geologists there over the years. Unfortunately, it's a couple hours walk to get in.
Okay.
That's one of them. The other one is Huckleberry Mountain, which is Huckleberry Ridge and Huckleberry Mountain are parts of the same topographic feature, which is just outside the south entrance, near where the Snake River comes out of the park on the south side. And again, it's a fairly steep hike up to it, but it's a spectacular exposure of the Huckleberry Ridge tuff, the 2-million-year-old tuff, which shows all three members, which were in place at slightly different times, but form a single cooling unit in that area. You see the contacts between them perfectly well exposed in what amounts to the head wall of a landslide that has sort of made a clean exposure of relationships that are ordinarily rather obscure and hard to see in the trees.